In this lecture, we will describe how to find the inverse Laplace transform when exponential terms are involved in the numerator of a linear time invariant transfer function. Remember, the exponential terms in the S-domain indicate a time delay in the time domain. So when you see the exponential terms in the S-domain, this means one thing: there will be a delay or dead time affecting the response. For example, this could be a transportation delay, as the case of a flow of liquids, or perhaps transportation delay of parts or solids along a conveyor belt, which is a typical example in food industry or in manufacturing plants. The importance of dead time to feedback control can be understood by considering an example such as steering a car in icy conditions fitted with perhaps summer tires. With dead time, the car would not respond immediately after the change in the steering wheel position or angle. Clearly, such a case, it would be difficult to drive and would require a skilled driver who could wait for the effect of a steering wheel change to occur. So next time we see e to the power of minus theta s, then remember there is some sort of dead time or delay going on between the input and the output. Let's consider the following transfer function or system response. And before we proceed, let's review some of the Laplace properties, especially the real and the complex shifting properties. So what's the real shifting property told us? That if you have a function in the time domain which is shifted by t0, you will get e to the power of minus t0s multiplied simply by the Laplace transform of the f of t. However, the complex shifting property tells us that if you have e to power minus a t multiplied by your function f of t, then you will arrive at a shifted transform with the opposite sign of a. Going back to our function f of s, as we said, the exponential terms indicate a time delay. The first thing we need to do is to collect the terms that have the same time delay. In our case here, we have only e to power minus s. That sort of term need to be collected, and all associated terms with it has to stay together with this term. Then you can perform partial fraction expansion for each time delay as appropriate, but in general you must do a complete expansion for each term involved. So once the partial fractions are done and the expression is simplified, remember when you do the Laplace inverse, the e to power minus s simply is translated as a delay by 1 unit of time. And as we've done in previous videos, we will double check our results using the ilaplace function in Matlab. Please do have the symbolic math toolbox installed. Check previous videos for more information. Comparing our hand-calculated inverse Laplace together with the results obtained by Matlab, It's clear that the results match nicely. Please note that the Heaviside step function is also known as the unit step function.